In this lecture, we'll further develop theories for finding zeros of polynomial functions. Now, all of these will revolve around our rational zero test, so let's recall that real quick. If we have some polynomial whose leading coefficient is an and whose last coefficient is a0, then we can find the rational zeros of our function by looking at this p over q form, where p is a factor of a0, meaning we can divide a0 by p and get an integer, and q is a factor of an. And we saw a couple examples of this, and we saw that in general we'll have a lot of factors to check. For every number we get the positive and the negative, and we have to look at a lot of fractions, and it's pretty terrible without any further help. So let's try to narrow down our field of search. And we'll do that by finding some other tests for zeros of a polynomial. So let's start by giving a definition. We say that a variation in sign occurs in a polynomial when two consecutive constants in a polynomial have opposite signs. So let's see what that means for our example here. What we do is we write down what each of our coefficients are. So our first one is 3, our second one is 2, our third one is -1, and our last coefficient is 5. And then we look to see where we change signs. So from 3 to 2, we stay positive, so no variation occurs. However, when we go from 2 to -1, we get a variation, since we switch from positive to negative. And then as we move again, we change from negative to positive, so we have another variation. So by looking at the coefficients, we see that we have two variations in signs. And we'll use this to find if we have positive zeros or negative zeros. And we do this by using Descartes' rule of signs. So let's say we have our standard polynomial, but now we need to make sure that the last term, a0, is not equal to 0. And that's not too much of a restriction. We can sort of factor out an x if that's the case and keep using it. If we have a polynomial like this, then we can actually find the number of positive and negative real zeros by just looking at the variations of signs. So the number of positive real zeros of f of x is either equal to the number of variations in sign of f of x, or less than that, by some even integer. This phrase here occurs when we have complex zeros. Remember, complex zeros come in conjugate pairs, so we always pick them up 2 at a time. So we might have to subtract off 2 if we have 2 complex zeros, or 4, but it's very useful, and we'll see how in just a second here. Now, if we want to find how many negative real zeros we have, we need to make one slight change. Now, this will be equal to the number of variations in signs of f of negative x. So we'll have to change all of our x's to be negative and see what happens. So let's do an example here. We'll find the number of positive and negative real zeros for f of x is equal to 3x cubed minus 5x squared plus 6x minus 4. So let's start. If we write down our coefficients here, we have 3, -5, 6, and -4, and we have a lot of variations in signs. We pick up 1 from going from 3 to -5. We pick up a second one from going from -5 to 6. And we pick up a third one going from 6 to -4. So we have 3 variations in signs. So this means we have either 3 or 1 real positive zeros. So we start with our upper limit of 3 here, and then we just have to start subtracting off 2 at a time, just in case we have complex zeros. But most importantly, we are guaranteed to have at least one positive real zero, and this means that if we're trying to factor it, we don't need to look at negative numbers. We can start by just looking at positive numbers. Now let's do the negative case. For this, the first thing we have to do is find what f of negative x is. And to do that, every time we had an x before, we need to change that to be a negative x. So our polynomial becomes 3 times parentheses negative x cubed minus 5 times parentheses negative x squared plus 6 times parentheses negative x minus 4. And if we look here, let's do another color. Any time that we have an odd powered exponent, this is going to change the sign. And every time we have an even powered exponent, everything's going to stay the same. We count minus 4 as being even, since I can actually write this as x to the power 0. And we consider 0 an even number. So negative x cubed becomes negative x. So this is negative 3x squared. Negative x squared doesn't change. So this stays as minus 5x squared. Negative x is odd, so this flips to be minus 6x. And the minus 4 doesn't change. So again, take a look here. All the odd ones change, and the even ones stay the same. Now if we look for our variations in signs, we actually have none. We are negative in every single term here. So we have 0, negative, real zeros. So we shouldn't even consider negative numbers when we're looking at our rational coefficient test. So this can really help us narrow it down, and we can actually either normally throw out all the positive numbers or all the negative numbers and cut down our potential zeros by half. We can even do a little bit better than this. If we use the upper and lower bound rules, we can actually find if the number we're picking is too big or too small, and we can use that to really narrow down and find the zeros we want. So let's say we have f of x, a polynomial with real coefficients, and importantly, a positive leading coefficient, which again isn't too bad. We can always factor out a negative number to change that. When we have these criterion, the next step is suppose f of x is divided by some linear term, x minus c, using synthetic division. When we go through this process, we'll find if the number we've picked is too big or too small, and start looking again. So what the rules say is if we pick a positive number for c, and each number in the last row of our synthetic division is either positive or 0, then c is an upper bound for the real zeros of f of x. That means our zeros are smaller than c. We need to start looking at smaller numbers than what we've originally plugged in. On the other hand, if c is less than 0, and after we do the synthetic division, the numbers in the last row are alternating between positive and negative, and we count 0 as either positive or negative, then we say c is a lower bound for the real zeros of f of x, and that means our zeros are larger than c. So we need to start plugging in bigger numbers to find our c's, and we don't have to worry about any of the smaller ones. Now this is a very powerful tool, if a little bit subtle, so let's practice it by finding these zeros of f of x is equal to 3x cubed minus 5x squared plus 6x minus 4. So let's get started. Whenever we do this, the first thing we want to do is our rational root test, or our rational zero test. So remember, a0 is equal to negative 4, and the factors are plus or minus 4, plus or minus 2, and plus or minus 1. These are all the integers that can divide 4 and negative 4 and end up with an integer. An is equal to 3, and 3 is a prime number, so this is actually just plus or minus 3 and plus or minus 1. And the numbers we need to check to be zeros are any of these combinations of fractions. So we have 1, 2, 3 numbers on top, 2 numbers on bottom, and each one we have to check for a positive or negative. However, remember from Descartes' rule of signs, we have at least one positive real zero so we don't need to worry about negative numbers. We just need to pick positive numbers. So we've ruled this down to the following. On the top, we can have 4, 2, or 1. On the bottom, we can have 3 or 1. And we only have 6 possible choices that we can make. So we've started at 12 and we've narrowed it down. Our choices are 4, 2, 1, or 4/3, 2/3, and 1/3. So let's pick a number in the middle and just sort of check it. Let's check to see if x equals 1 is a 0. And we can do this with synthetic division and just see if we have a remainder of 0. So here, x equals 1 is our 0, so I can write this as factor x minus 1. So I put 1 outside the box, and inside the box go the coefficients of our polynomial. So these numbers right here, 3, negative 5, 6, and negative 4. 3, negative 5, 6, and negative 4. Checks out. We perform our synthetic division and see what we can do. So 3 goes outside the box. 3 times positive 1 is 3. 3 plus negative 5 is negative 2. Negative 2 times 1 is negative 2. Negative 2 plus 6 is 4. 4 times 4 is 0, and it checks out. Since we have a remainder of 0, then this says we can factor out x minus 1, and we'll be left with 3x squared minus 2x plus 4. Let's see what would happen if we picked a larger number than 1 and did the synthetic division. So maybe we'll do this in a different color. How about we do it in purple here? And why don't we try dividing by 2 and seeing what the outcome will be. We carry down 3. 2 times 3 is 6. Negative 5 plus 6 is 1. 1 times 2 is 2. 6 plus 2 is 8. 8 times 2 is 16. Negative 4 plus 16 is 12. These numbers are all positive, which means we need to look at smaller numbers. We know the answer is already 1, so this checks out with our theory, and we can see that if we have all numbers down here, we need something smaller. Okay, let's try this again with something smaller than 1. How about, let's do 2/3. Okay. So 3 goes outside the box. 3 times 2/3 is 2. -5 plus 2 is -3. -3 times 2/3 is -2. 6 plus -2 is 4. 4 times 2/3 is 8/3, which we can abbreviate as 2 2/3. And -4 plus 2 2/3 is -1 1/3. And now we look, we have a positive number, then a negative number, then a positive number, then a negative number. So these are all not positive. If we even have one negative number, that means that this is not an upper bound. This means we need to look for a larger number. If 2/3 was an upper bound, then we would expect all of these numbers to be positive. Since it's not, then that means we need to look for a larger zero, and we know what it is, it's 1. But we can use these to start narrowing down. If I plugged in 2 and I saw, okay, I got all positive numbers, I should pick something smaller. Then I picked 2/3 and I saw that I didn't get all positive numbers, I got some negative numbers, and that means I need to go up. So I didn't need to check 1/3, but I'd still have to check 4/3 and 1. So with 2 steps, I've sort of thrown out the bigger numbers and the smaller numbers and narrowed it down to the right answer, which is 1. So let's do another example, and let's put it all together. Again, the first step is always using the rational root test. A0 is equal to -2. The numbers that divide -2 are simply plus or minus 2 and plus or minus 1. AN is equal to 6. The numbers that divide 6 are plus or minus 6, plus or minus 3, plus or minus 2, and plus or minus 1. Here's all our potential candidates, and it turns out we have 16 of them. Once we've done this, we move on to Descartes' rule of signs, and we check the variations. So for f of x, our coefficients are 6, -4, 3, and -2. So we have a variation between 6 and -4, -4 and 3, 3 and -2. This means we have 3 or 1 positive real zeros. Remember, we start subtracting off 2 in case we have any complex zeros. F of -x, if we remember our shorthand, the odd ones change signs and the even ones stay the same. That's pretty easy to calculate. 6x cubed becomes -6x cubed. Our x squared term doesn't change, so that's minus 4x squared, minus 3x minus 2. And we can quickly look and see that we have no variation in signs. So we have 0 negative real zeros. So we just need to look at 2 and 1 on top, and 6, 3, 2, and 1 on bottom. Okay. Finally, we move on to the upper and lower bound test. We just start plugging some of these in and seeing what we get. So maybe we'll write the polynomial again so we don't lose sight of it. It was 6x cubed minus 4x squared plus 3x minus 2. And let's try to factor out x equals 1. So So we make our box. We put down our coefficients. We do 1 outside. And let's start working. 6 goes outside. 6 moves up. -4 plus 6 is 2. 2 moves inside. 3 times 2, or 3 plus 2 is 5. 5 times 1 is 5. -2 plus 5 is 3. And that means that this is an upper bound. So we don't need to try any numbers bigger than 1. We need to start looking at fractions. So let's try another fraction here. How about we try 1/2? Six goes outside. 1/2 of 6 is 3. -4 plus 3 is -1. A half of -1 is -1/2. This becomes positive 2.5. Then this is what? 5 halves. So this becomes 5/4. And this becomes 3/4. But notice here, we have a negative number. So we need to look for larger zeros. This wasn't an upper bound, so that means there is a zero that's bigger than 1/2. So let's try 2/3 here. Six goes outside the box. 6 times 2/3 is 6 again. Sorry, not 6. 4. -4 plus 4 is 0. 0 times 2/3 is 0. 3 plus 0 is 3. 3 times 2/3 is 2. And -2 plus 2 is 0. We have remainder 0, so this is a factor. So we factor out x minus 2/3. And this simplifies down to 6x squared plus 0x plus 3. And we've done it. Once we saw 1/2 wasn't an upper bound, we didn't need to check 1/3 or 1/6. So actually the only number left that it could be was 2/3. So by just checking these three numbers, we were able to get a very good idea of where our zeros should be. They had to be smaller than 1, but bigger than 1/2. If we wanted to find the other two zeros, we could simply set 6x squared plus 3 equals 0. And then we'd get 6x squared is equal to -3. X squared is equal to -1/2. And x is equal to plus or minus the square root of -1/2. Or x is equal to plus or minus the square root of 1/2 times our imaginary number I. And then we have our three zeros right here. 2/3, square root of 1/2 I, and negative square root of 1/2 I. All combined, these three techniques allow us to really narrow down and find our zeros pretty easily. So we'll practice a little bit more with these in class, and we'll see in particular how the upper and lower bound test really helps us out.